Hi, welcome to the elasticity class. Today we are going to talk about how bodies deform, how we measure how much they deform locally, and we are going to introduce the idea of an engineering string. This will be done in such a way that it works both for small deformation and finite deformation. You've probably seen some version of this in your earlier strength of materials class, but again this is a more serious version. So let's get started. So our basic idea is the following. When external loads are applied to bodies, they deform because internal forces are created which cause bodies to change their shape or orientation. We need to monitor local shape changes because they are the means by which we figure out the stresses. What we mean by that is, actually it's only the internal deformations that we can measure. We cannot really measure the stress directly. We kind of figure out the stresses by doing some correlation between deformation and stress. So any measurement of force ultimately boils down to measurement of deformation of some kind. This is very fundamental. So we have to be able to figure out how to measure deformations. Okay. So the way we do it is by creating a grid of small triangles, small right angle triangles, and monitoring how they deform. Let me show you what I mean. Okay, so I'm going to play this particular video which shows how a triangulated body actually deforms into like a bent shape, and you can see what happens to particularly marked triangles. Okay, watch this one and pay attention to the red and blue triangles. Watch, can you see the three red triangles and see how they get deformed? They're getting stretched further and further out, they're changing shape and so on. So if you really want to see this, I'm going to put them kind of side by side. So if you look at this original triangle here, it has become this funny looking triangle there. This original triangle there has become that triangle. This triangle here has become kind of it's not moved, it has not changed much. So you could say not much deformation has occurred here, quite a bit has occurred there, this something strange has happened here and so on, and you can see how the whole thing has got bent. Okay, this is just an illustration of what we are talking about. Just wanted to show you what how these deformations actually work. So let me turn all this thing off. We don't really need MATLAB. Okay, so now we have an idea of how things deform and what they do and so on. So now we are going to look at, excuse me, so that I have space. There you go. Okay, so what we do is, if I start out with a right angle triangle like that, it seems to kind of deform out and become something else. A, B, C becomes maybe little a, maybe little b, maybe little c. To see how this occurs, we can think of it as three different successive stages. What do I mean by three different successive stages? So we start out, I'm going to start out with a small triangle, and it's a right triangle, both sides equal, so it's isosceles right triangle, so it's a fairly small triangle. What the first stage, I'm going to imagine that it gets much longer like this and kind of shorter like that, became like that. Okay, this is stage 1, and here things gets elongated or shortened without changing the right angle, this angle, right? So A, B, C becomes A prime, B prime, C prime. Next, we are going to imagine that it gets sheared. So when it gets sheared, what I'm expecting is A prime, B prime doesn't change. C prime was originally here, no? So what has happened is C prime kind of moves here. So C prime was here, now it has become A double prime, B double prime, C double prime has gone there. Sorry, let me draw this carefully so that we don't make a mistake and make some special assumptions. So I'm going to draw C prime here, and it has become like this. Okay, to see what has happened, I'm going to draw the right angle, and we're going to draw this angle like that. Can you see how much it has sheared? Or I can draw it here, you can see that, like that. What used to be like this. So that's shear. Third one is rotation. So what has happened is, instead of being this way, it has now become like that. Okay, these two involve change in shape. This last one involves rotation. And what we want is our measure of stream should be able to quantify shape change and ignore rotation. So what I mean by that is that if there is no stretch, no shear, then no strain. And it has to go both ways. So bottom line, you can imagine any local deformation can be thought of as stretch it, shear it, rotate it. That's how it works. Okay, so this is the end of this module. So now, last module we saw this little thing about how to deform something, and I talked about taking a little triangle and stretching it, shearing it and rotating it, right? Now we are going to figure out how to measure it by starting out with a very simple one. Look at a simple straight line segment. What I mean by that is, let's say I had an initial object that looked kind of circular and it has now become somewhat elongated, right? And I had a small line segment here, AB, that has become something else there, little a, little b. Please remember, if the line segment is large, it won't become a straight line. Only short line segments will be almost straight. The shorter, the straighter. This is what I want you to remember, okay? Only short line segments will remain straight, the shorter the straighter. So what we are going to do, let me move this down a little bit. Oops. There you go. Is to say, okay, our x and y coordinates are like this. Our x and y coordinates are like this, and we are going to call this delta x, that's delta y, and we have the following thing: location of A, of capital A, is at x comma y. Okay, capital AA is displacement of A, which is equal to displacement vector at x comma y. Location of B, x plus delta x, y plus delta y. BB equal to displacement of B. Which is equal to u of x plus delta x, y plus delta y, which is approximately equal to u of x comma y plus u comma 1 delta x plus u comma 2 delta y. You see what I did, right? It's a simple Taylor series. But this is that, and so you will get ub minus ua equal to u comma 1 delta x plus u comma 2 delta y. Now comes the very interesting thing. Little a, little b is what we are really after. What has happened to the line segment? Capital A, capital B we know. So what is this? What's this vector? And that's easy to find out. Little a, little b equals AB plus BB minus AA. You can see that. You can draw the vectors and you can see. This turns out to be, well, we know what is AB, delta x I plus delta y j plus this is here u comma 1 delta x plus u comma 2 delta y, which turns out to be 1 plus, sorry, I plus u comma 1 delta x plus j plus u comma 2 delta y. So this one is called the F1 vector and this one will be called the F2 vector. Let's see what the F1 vector looks like. It's I plus u1i plus u2j plus u3k comma 1, which is I plus u1 comma 1 I plus u2 comma 1 j plus u3 comma 1 k. So I can write this like a column vector. F1 column vector will look like 1 plus u1 comma 1 u2 comma 1 u3 comma 1. F2 will look like, if you do the same thing, u1 comma 2 1 plus u2 comma 2, sorry, there is no u3, excuse me. So I can write this whole thing, matrix AB, the column vector AB looks like 1 plus u1 comma 1 u1 comma 2 u2 comma 1 1 plus u2 comma 2 times delta x delta y. This matrix is called the F matrix and its technical name is deformation gradient. In fact, you can see I can write this in an even nice way, which is very useful. Nice, no? This is nothing but gradient of u. So after all of this, we got a very nice result. The column vector AB equals identity matrix plus gradient of u, which is the Jacobian of the displacement, times the column vector of AB. So let me write it down. Final column vector equals identity plus Jacobian of displacement field. This is another name for saying gradient of displacement times original column vector. So everything is hidden here. In the next class, I will talk to you about calculating strain, change in length over original length and all of these things. Okay, thank you.